Hi folks, so this is our last video for the chapter 11 content. So we just were talking about liquids and solids in chapter 10, and we were talking about pure liquids. But many chemical reactions and certainly a lot of important biological processes actually occur in solution. So remember we talked about solution right at the beginning of the semester, right? A solution is, the solvent is the major component, so what has the greatest quantity in terms of moles, and then the solute is the minor component. And remember, we can have multiple solutes, okay? Also the solvent doesn't have to be a liquid, it could be gas, so like air is a solution of gases, right? The major component in air is nitrogen. So in this chapter, we're talking about aqueous solutions mostly, and mixtures of volatile solvents. So when we're talking about ionic compounds, if they're soluble, we categorize them as electrolytes. So they dissociate completely in aqueous solution. They break up into their constituent cation and anion components. When something is molecular, remember we talked about molecular compounds before, they do not break up into cation and anion into aqueous solutions, okay? They just swim around in big chunks, like sucrose would be a great example of that, okay? Any soluble molecular compound is what we call a non-electrolyte because it does not break up into ions. So thinking more about ionic compounds, so what holds ionic compounds together in terms of intermolecular forces are those ion-ion attractions. And the magnitude of these ion-ion interactions is described by the lattice energy, which basically follows like Coulomb's law. So lattice energy is stronger if the charges on the ions are greater, and if the distance between them is smaller, which if there's smaller distance between them, that means they have smaller ionic radii, so their bond length is shorter. So we can calculate the lattice energy using a Born-Haber cycle relying on Hess's law, it doesn't matter what route you take to get from point A to point B, just that you sum up all the steps to get from point A to point B. So when we're dissolving an ionic solid in water, the way by which this happens is ion-dipole interactions, if we're thinking in terms of intermolecular attractions. So each cation that is coming out of the ionic solid then would be hydrated by the water molecules, so we call this a hydration sphere, and it's important which way the water molecules are oriented, right? Think of what a water molecule looks like, okay? So we've got the oxygen in the middle with two lone pairs on it, and then we've got two hydrogens coming off to the center of that molecule. One side is delta minus, and then where the hydrogens are, that's our delta plus side. So the cation will be surrounded by the delta minus side of that dipole, the oxygen side, and then each anion in solution will have the positive end, the hydrogen delta plus end, forming the hydration sphere around it. So when we're talking about gases, they can also dissolve in a liquid solvent. Okay, that's how fish can breathe, right? Because oxygen's dissolved in water. And this happens when the gaseous and liquid phases have similar intermolecular forces. So we can calculate how much gas will dissolve at a given partial pressure. This relationship is described by Henry's law. And that states that the concentration of the gas is equal to the partial pressure of the gas multiplied by the Henry's law constant for that gas. I'd give that to you in a table or whatever. So when we are talking about solutions, one very important thing to discuss is colligative properties. So these are characteristics of the solution which only depend on the concentration of the solute particles, not on the identity of whatever those particles are, okay? So it doesn't matter if it's a sugar solution or a salt solution, unless you're gonna drink it, right? So the most important ones we're gonna discuss in this chapter are vapor pressure lowering, freezing point depression, okay, two sides of the same coin, right? Boiling point elevation, and osmotic pressure. So these solutions have different properties to the pure solvent, okay? So when we dissolve a non-volatile solute in the volatile solvent, that is gonna lower the freezing point and raise the boiling point for that solvent compared to if it was pure. And the reason why this happens is because it affects the vapor pressure of the solution. The vapor pressure for the solution is lowered than it is for the pure solvent. This is vapor pressure lowering. So we can calculate the effect of this using Raoult's law. That allows us to calculate the vapor pressure of the solution. So what we do is we take the mole fraction of the solvent out of the total number of moles of solution, and we multiply that by the partial pressure of the solvent to find out by how much the vapor pressure has been attenuated. We can also apply Raoult's law to homogeneous mixtures of volatile solvents. So if we've got several volatile solvents, you can just use the product of the mole fraction and partial pressure for each component, okay, so for each solvent in the mixture, and then sum those all together to get the overall vapor pressure of that mixture of volatile solvents. So Henry's law and Raoult's law both apply to ideal solutions, okay, so think about what we learned from ideal gases, right? So an ideal solution is describing that vapor phase above the solution where the mixture of gases in that vapor phase are following ideal gas assumptions. So we do see deviations from this ideal solution behavior, and it's all to do with intermolecular forces. So when we have solvent-solute interactions that are either much stronger or much weaker than the solute-solute or solvent-solvent interactions is where you would see deviations from ideal solution behavior. So when we're talking about colligative properties quantitatively, there's something very important you need to learn. We've learned about molarity. So that's capital M, moles per liter. Right at the beginning of the semester when we were talking about quantifying chemical reactions and stuff. And now we have to also learn about molality, which is small m, and that is moles per kilogram. These are both just two different ways to mathematically express the concentration of a solution, okay? So molarity, moles per liter, molality, moles per kilogram, okay? So that's the difference between the two, okay? It's how you describe the amount of solvent. Okay. When quantifying the effect of our colligative behavior, we are going to use molality for freezing point depression and boiling point elevation calculations. So the amount the boiling point of the solution is elevated or the freezing point is depressed is proportional to molality. The constant of proportionality is either the boiling point elevation constant or the freezing point depression constant, depending on which one you're talking about, right? So for a molecular compound, all you need to do to calculate the delta T, the amount that the boiling point is increased by or the freezing point is depressed by, is just multiply this constant of proportionality by the molality of the solution. Okay, if we have an ionic compound, we've got to take into account the fact that ionic compounds are going to fully dissociate into cations and anions. So we need to add one more thing, which is the Van 't Hoff factor, which is called I is the letter for it, and that basically describes the number of free ions produced from dissolving 1 mole of the ionic compound, okay? So if you have 1 mole of sodium chloride, that's going to give you 1 mole of sodium ions plus 1 mole of chloride ions, so then I would equal 2 for 2 moles of ions. If you have magnesium chloride, MgCl2, you get 1 mole of Mg2 plus cations and 2 moles of chloride anions. So 1 plus 2 is 3, I equals 3 for magnesium chloride. So do be careful when you're looking at ionic compounds. You have to take into account how many cations and anions are formed. So the last colligative property we need to describe is osmosis, which you've probably come across before in bio at some point. Osmosis is the flow of a solvent across a semi-permeable membrane. So that means the membrane will let solvent particles through, but not solute particles, because the solute particles are bigger, okay? So they will flow across the semi-permeable membrane to balance the concentration of the solution, okay? So we'll have a more concentrated solution on one side and a more dilute solution on the other side. The solvent is going to be what crosses the barrier from the more dilute solution to the more concentrated solution to dilute that more concentrated solution until the two solutions have the same concentration and equilibrium is achieved. So at equilibrium, the solvent is still going to flow across that barrier, but it's going to be the same in both directions, so it cancelled out. So if we are going to quantify osmotic pressure, instead of using P, we use pi, but it's still pressure, right? And that is the pressure required to stop the flow across the membrane. And this is a colligative property. It only depends on the concentration, not the identity of the solute. So we can rearrange the ideal gas law, our friend PV equals nRT, and substitute when we get N over V, that is molarity, big M, right, N over V. So we end up with the expression pi, our osmotic pressure, is the molarity times the gas constant times the temperature. And don't forget, we're really awesome at moles calculations now. If you know the number of moles of solvent, the number of moles of solute and the mass of solute, of course, you can calculate its molar mass. Okay, so that is it. We've got to the end of Gen Chem 1. I'm sorry I wasn't there in person to enjoy it with you guys. And I'm still around, right? Even though this is my last video, I'm still around in my office hours and our remaining lectures this week. So drop in, I'll be around on GroupMe as well. I'm hoping you're enjoying some of the Cockney rhyming slang. Seemed a shame not to continue learning some of that. You never know, we might get to travel sometime, right? Okay, so I'm gonna miss you guys, and yeah, good luck in your finals. You're gonna be awesome. I can't wait to see how great you all do. Okay, take care, have a good summer. Things will get better soon. Bye.